Okay, so today's lesson is on 26.9, which is the nuclear radius. So you need to be able to describe how the radius of a nucleus depends on its mass number A, and be able to calculate and describe the density of a nucleus. You can determine the size of a nuclear radius from electron diffraction. So if you fire a beam of high energy electrons at a thin solid sample of an element, the incident electrons are diffracted because they have a de Broglie wavelength, and it's of the order 10 to the minus 15 or a femtometer, and that's about the same diameter as a nucleus. And you need to remember that the de Broglie wavelength is evidence of particles behaving like a wave, which is why the electrons can diffract. A detector is used to measure the number of electrons per second diffracted through different angles. So they'll put the detector at an angle, measure how many electrons are coming through, then move the angle, measure the number of electrons, etc., etc. So here's your electron beam, here's your detector, and you move it through the different angles, and you can measure how many electrons are being received by the detector. So how does that enable us to determine the size of the radius? So these results show the graph, and what they actually show is an angle theta minimum, and that's when the number of electrons per second decreases to a minimum and then increases again slightly. So what's happening here is the same as a diffraction pattern with light, that here, because the electrons are behaving like waves, there is cancellation and you are getting a minimum, okay? So that minimum, that theta minimum, is where you are getting the least number of electrons per second. And so the electrons are scattered, they interfere with each other, creating maxima and minima. And theta minimum is the angle of the first minima from the centre. Now the wavelength of the electrons that you are firing is equal to hc over E. I'll just show you why that is. The de Broglie wavelength is h over mv. Okay. Now h over mv is almost like E equals mc squared. Okay. Where I've just changed the c here to v to match with this. They're almost the same, but not quite, because you've got this squared term. I want to make mv into E. So in order to do that, to make mv into E, I've got my mv squared term here, which is E. And then if I was to divide through by v, that would give me mv again. So that enables me to do this. Lambda is h over mv. mv is equal the same as mv squared over v. They're the same thing. So I've substituted that in there instead of mv. This v will go to the top, so you get hv over mv squared, and mv squared is the same as E. So I've substituted E in there, and then I've just put the C back for V. So this is an alternative way of looking at the de Broglie wavelength, where the wavelength is equal to hc over E. If you don't get this, don't worry too much. It's just, and they do this a lot at A2, this nifty trick of converting basically momentum into energy. Okay. So if we look at this equation, this is the equation for diffraction that we did in waves. So n lambda equals d sine theta. And what I'm going to do is substitute this equation in here for lambda. And also at the first minimum, n is 1. So that gets rid of the n term. So you end up with, I've sort of missed, I've missed a stage here and just rearranged it. But your lambda would be hc over E equals d sine theta. So hc over E equals d sine theta, and then I've rearranged for d. So that will give you the spacing of the minima. So it's basically the diameter of a nucleus. So that d is the diameter of the nucleus, because that's what's causing the diffraction. So each spacing between the minima is one whole atom, if you like. So let's have a look at how that works. So I'm going to use H is 6.626 times 10 to the minus 34 joules seconds. I'm going to use this equation here, D equals HC over E sine theta minimum. And it says, what is the nuclear radius when the electrons have 420 mega electron volts and theta minimum is 44? Now this D is the diameter, so whatever you get out you're going to need to halve, and it's also in meters. Because it's in meters, which is a standard unit, you can't have mega electron volts, you need to have joules. So let's see what I've got. I've got H, that's a constant, and I've got C, that's a constant. I've been given E as 420 mega electron volts, so I'm going to convert that into joules. So I get, so mega charge of an electron, 1.92 times 10 to the minus 11 joules. Now my theta minimum is 44 degrees here. Substitute all of that into this equation, so I get HC over E sine 44, and it comes out as 4.023046401 times 10 to the minus 15. Again, that's the diameter of the nucleus, so I just need to halve it. So I get 2.0115232 times 10 to the minus 15. And then, that's three significant figures. If you check in the book, I think it gets a slightly different answer, but I think it might be wrong. I think this is right. I've done this several times, and this is the answer I get every time. If you do it and discover that you get a different answer, let me know. So that's using that equation. You can also determine the radius of the nucleus by using this really nifty equation, which you are given. By using different samples of different elements, you can determine the radius R of different nuclides, which is what they did. And come up with this equation. R equals a constant, which is called R0, A to the third. So what this tells you, what you're actually doing is what this is doing is, this is the size of a nucleon. Then you're multiplying it by how many nucleons you've got. But because those nucleons will be arranged in a 3D sphere, you then do to the power of a third to get one dimension. So it will give you the radius in one dimension, rather than if you multiply it by 8, it would give you all of them in a 3D shape. Okay, so by taking that third, you're just finding a single dimension. If you were to plot a graph of R on the y-axis against A to the third on the x-axis, you get a straight line. If you plot a graph of R against A, you get a y equals x to the third graph. Okay, so you need to plot it against A to the third. It'll go through 0, and you also get the gradient here as R0. So that's what they did. They plotted this graph, got a gradient of R0. You can also plot log graphs. So log graphs turn things to the power into straight lines. So if we have a look at this log graph, just move me out of the way. So all I've done is take natural logs of this equation here. So log R, R0, because they're multiplied together, the plus comes there, which is a rule of logs. So you're going to get log R0. I've moved it over there, plus, because it helps me my y equals mx plus c. And then this a to the third term becomes 1/3 log a. So I'm then going to plot a graph of log R, y-axis, log a, x-axis. And here, this is my c term, log R0. So the y-intercept gives me log R0. And the gradient should be a third. So this is a different method of finding R0. So you would take the value here, log R0, let's say that's 10. Log R0 is 10, and then you do e to 10. Get the right answer. So, example of using this equation. What is the nuclear radius of an atom of iron? So iron has an A, a relative atomic mass of 56, so it's really simple. You literally just plug the numbers in. So you got R equals R0, which is 1.05 times 10 to the minus 15 times 56 to the third. Comes out as that, which is 4.02 femtometers. So this way is much easier than the other way. Last thing I want to talk about then is the nuclear density. So assuming that a nucleus is spherical, the volume of that nucleus will be 4/3 pi r cubed. If we substitute this equation we've just looked at in for r, we'll get the volume is equal to 4/3 pi r0 a to the third cubed. If you expand out this bracket, that becomes 4/3 pi r0 cubed a. Now, volume is proportional to the mass of the nucleus, which means the density is constant no matter the size of the nucleus. So basically, the only thing that determines the volume of the nucleus will be the mass of the nucleus. These are all constants. So if we have a look at this, density is mass divided by volume. So the mass is A. To convert it into kilograms, you need to convert it to times it by U. So that's why that U is there. So A times U gives you the mass in kilograms, divided by 4/3 pi r0 cubed A. And if you notice, the A's cancel. So you get 3U over 4 pi r0 cubed. All of those things are constant. So the density is constant. So nuclear density does not change the different elements. So let's just show you an example of using this. 1U is 1.661 times 10 to the minus 27 kilograms. You get given that in the data sheet. So what's the density of the nucleus? So density is 3U, so 3 times 1.661 times 10 to the minus 27, divided by 4 pi r0 cubed. Okay. 3.4 times 10 to the 17. These are the questions from the book. I want you to have a go at them, and then if you haven't got the book, the answers are on the help video where I'll go through how to do them all. So if you're struggling, you can have a look at that. Okay, bye.